I guess kind of wanted to just talk a little bit about what this class is and what it ain't. um, so, we're going to talk about a few different kinds of engines, but we're mostly going to focus on the modern four-stroke engine because that's what is used most often. Um, and I guess we'd really like it, if when we're done here, everybody has a little bit of an idea of what's going on in there, and but don't expect to be, um, the country's authority at the end of this class because, honestly, it's something that it would take a much more in-depth class than this to be a real expert. But, you know, um, probably have a lot better idea what's going on with your pickup and things like that at the end of this class is kind of the idea. And have a little better idea um, what you need to do when something goes wrong. Um, so, kind of like the handout there says, by introduction, this means that this class is just the beginning. Um, I went to school full time for 2 years. Well, shucks, somebody needs to turn their ringer off, huh? Um, and then, worked in shops full time, and um, I guess I've been working in this industry full time for 28 years, and work on engines every day, and I still learn stuff. Um, so talking about internal combustion engines. So, what makes an engine an internal combustion engine? Can you think of something that would be an external combustion engine? Any ideas? Yeah. So I guess what I was kind of getting at there is, like you said, the stuff that starts it's on the outside. So like rockets, those are engines. Jets, those are engines. Um, Hi Cole. Um, Steam engines, those are engines. Um, but the combustion, the explosive burning of fuels, isn't on the inside. So we're not going to be talking a lot about jets, and we're not going to be talking a lot about rockets. And steam engines use steam that's preheated or superheated by an external heat source. Um, so we won't be talking a lot about those. Although if you have a question about one of those, we might try and entertain it when we have a little bit of time. Um, but internal, so we're talking about engines that the combustion, which like we say here is the rapid expansive burn of fuels, that happens on the inside of the engine. So on a jet, it's happening on the outside. On a rocket, it's happening on the outside. Um, on a steam engine, it's happening in a separate firebox. But on these engines, the fire happens inside the engine. Um, and the term combustion um, is something we want to talk about for quite a little bit tonight. And part of the reason for that being, if you understand what's actually going on in the combustion, you have a lot better idea why we make some of the parts of the engine do what they do. And if that combustion ain't working right, you'll have a little better idea, well, what part of the engine may be causing that to not happen. Um, but when we're talking about combustion, we're talking about taking fuel and oxygen and having what some would call a chemical reaction, which it is, fire kind of is. You want one, dear? Fire kind of is a chemical reaction, right? We're taking a molecule of this and a molecule of that, and we're scrambling them and getting molecules of something else, right? And so what comes out of combustion is different things than what we put into it. We also get heat, and what we're really after in these internal combustion engines is the rapid expansion of the gases. Is that rapid expansion is what we're using to push on the piston and create work. The heat helps with that rapid expansion, but we get a lot more of it than we need, and we got to get rid of a lot of it. And so we'll actually talk about cooling and how we get rid of that extra heat. But I guess wanted to take a couple of minutes here and talk about what's actually happening in this combustion. So before we get into that, I guess you'll notice here on the I guess you call it a class syllabus here. At the end of it, it talks about what subjects we're going to have each week. And that's kind of a guide. And gosh, guys, I love it when you ask questions. So if you have a question, feel free to wave at me and, hey, we'll talk about it. Because the class is only an hour, why we kind of need to stay a little bit on subject. And if it's something that I think we're going to be talking about in another class anyways, I may say that. And hey, don't be offended, and don't be afraid to remind me later, but feel free to ask questions, all right? But you'll notice on week 6, there's an item there that says student request. So if you look through this list and there's something you're interested in talking about and it ain't on the list, tell me about it, and that might be what we talk about on week 6, okay? You'll also notice that it talks about quizzes. So at the end of each class, we're going to have a quiz. It's totally voluntary. If you don't want to play, no sweat. But if you would take the quiz, it does 2 things. Number one, if I get the quizzes back and half the people got a question wrong, it tells me that, hey man, I did a really bad job of explaining that, and I need to fix that. But also it's just kind of for fun. And hi guys. Hey, we just got started. You didn't miss a lot. Most of what you missed is explained on these handouts, so feel free to grab a chair. And we were just talking about, I guess we were down to here. So at the end of class, I'll hand out a quiz. If you feel like taking it, great. If you don't, no sweat. But some of the local tool dealers have donated some fun prizes. And so everybody that wants to turn in a quiz at the end of class, why, at the beginning of class next week, we'll give a prize to, the best score on the quiz. And there's actually a nice little tool set that's been donated, and whoever gets the best scores on the quiz over the whole class. There won't be a quiz on week 6 because I don't want to try and grade it during class. So that at the end of classes 1 through 5, there'll be quizzes, and at the beginning of the next class, we'll hand out the prize. And Caleb is videoing the classes, so if you have stuff going on with family and whatnot and you miss one of the classes, you can go get on YouTube and watch it and kind of catch up. Hi Wayne, how you doing? That's okay, no sweat. So glad you're all here. And like I said earlier, wanted to take a little bit of time tonight and talk about the combustion. Because if we really understand what's going on with that combustion, We understand why the different parts of the engine are there to begin with, and what they do to aid the combustion or work with it. And if we understand all that, then it helps us figure out what's wrong when the combustion ain't happening the way we want it to. So I know if you don't like chemistry, well, you might grit your teeth here a little bit, but I think if you'll just follow along a little bit, it'll help a lot of the rest of this make more sense. So in these internal combustion engines, what we're using for fuel is all known as hydrocarbons. Gasoline, diesel fuel, propane, methane, you name it, they're all compounds that are hydrogen and carbon. So, for example, the most common form of diesel fuel is known as C14H20. So what a molecule of that looks like is it's got a whole string of carbons, and I should be making those C's, sorry. It's got a whole string of carbons that are linked together down the middle of it. And I'm not going to sweat the right number, it's just kind of the idea. And then branched out from this, like this, are, I drew the wrong thing, hydrogens. So you got hydrogen atoms like this. Okay, so you get the idea, right? Does that make sense? We got a bunch of carbon, a whole string of carbon, and branched out from it, we got all these hydrogens. And it's more or less the same, just different counts, all the different things we're talking about using for fuels. Interestingly enough, there's one kind of odd deal to that. Biodiesel, you get down to the end of a string like this, and it'll go off like this and have an oxygen, and usually have a leg like this with an oxygen, and have some hydrogens out here. So that's one kind of off-breed variation. And there's a few odd things happen because of those oxygens, but other than biodiesel, everything we're working with as fuel has those. And what we're ideally wanting to do is we want to work with oxygen and our hydrocarbons. And when we make that reaction, if you have perfect combustion, which we don't live in a perfect world, there was only one perfect thing ever, and that was Jesus Christ, and so everything else is imperfect. But in perfect combustion, you've got to, we're going to take those, we're going to take the hydrogens out of here and some of this oxygen, and we're going to make that. Anybody recognize that? Water, right. Then we're going to take some of these carbons and some of these and wind up with, anybody recognize that one? Carbon dioxide. So any engine that's running pretty much right, you're going to wind up with a lot of this and a little bit of stuff from the imperfect part of the combustion. There's going to be some that doesn't make the full reaction to CO2, and it's just CO. Anybody recognize that one? Carbon monoxide. So, for example, if when we're putting together our hydrocarbons and our oxygens, we've got what's known as a lean burn, we don't have quite enough fuel. I think I said that right. Anyways, no, the other way around. We don't have quite enough oxygen. I said it backwards, I'm sorry. We don't have quite enough oxygen, or we have not quite enough heat energy to complete the reaction. We wind up with some carbon monoxide, which y'all probably know that carbon dioxide is harmless. If you've drank a soda pop today, you've had an upfront encounter with carbon dioxide. It's what's in all our drinks, right? And as long as there's not too much of it that it displaces all the oxygen and you can't breathe, why, it's really pretty much harmless, right? Carbon monoxide, on the other hand, it tends to take up residency in your blood cells, and you can't absorb oxygen, and pretty soon you keel over dead. Yeah, with your tongue hanging out like that. So we'd rather not make carbon monoxide. And of course, the H2O we're making, it's well, there again, we're creating this in a burning reaction, right? And go ahead, Pat. Well, on the diesel, the white smoke is typically lean, and there again, it's incomplete combustion. And the black smoke is when, there again, this reaction is out of balance, and we wind up with a bunch of straight carbon. Right, when you've got an injector that's stuck open and you've got way too much fuel and not enough oxygen, and there's a whole bunch of different things we get from incomplete combustion. And I'll make a little list of them here just for fun, but the black smoke you get out of a diesel when either you've got an injector that's stuck open or you stomp on the throttle and your injection pump is squirting a bunch of fuel, but your turbo hasn't caught up to push enough oxygen, and you get that belch of black smoke right when you jam on the throttle. That's what that black cloud is. It's well, and there's going to be some C12 and some C14, but a lot of it's going to be C13. But anyways, it's different ions of carbon, and it's because we didn't have enough oxygen. Honestly, right at this second, I can't think of the exact reaction that happens that creates the white smoke, but it's the result of the fuel being injected at the wrong time, where the temperatures are out of whack. And because there again, to make this reaction all happen the way we want to, we got to have the pressure right and the temperature right and the right balance of oxygen and fuel. And if you've got way bad white smoke, it's a lot of time, it can be a lean burn, but it can also be the fuel being injected too late after the pressure started to drop, and we don't have enough pressure and temperature. Well, yes, both. Both, actually. Because if the injector isn't reacting rapidly enough, it can be what causes that. But there again, yeah, timing, timing of the fuel pulse, whether it's a result of timing per se or a lagging injector. But yeah, so some of the, other than the carbon, some of the things that we get from a byproduct of imperfect combustion is, in some cases, you'll get some hydrocarbons coming straight through that didn't react at all, which is not ideal. And actually, in that black cloud from when you stomp the throttle, you'll have some hydrocarbons that are stuck on straight carbon molecules, and that's actually what makes a lot of the black soot that you've probably been around when a oxyacetylene torch like that You know, a guy first strikes it and you get that puff, and there's them little fingers of black soot that are floating around. Well, and that's what makes is a big part of the black cloud, or the brown cloud, I should say, over the big cities, they say, is those little fingers of soot. And so the soot winds up being some unburnt hydrocarbon stuck on a carbon strand and making a stuff that's unpleasant to breathe, right? One of the other things that, well, we talked about the carbon monoxide, but another one that, you know, the EPA is real concerned about, and I suppose we should be to a certain extent too, is so who can tell me how much oxygen is in common air like what's in this room? Is it 10%, 20%, 50%, 80%? Any guesses? Not a bad guess. Did I hear something else? Well, it's right between you two guys. It's right in there, around 20 to 22% of common atmospheric air is oxygen. What makes up the biggest share of the rest of that air? There's some of that, and that's, you know, we get a lot of that from our green plants, but it's not the biggest piece. Right, nitrogen. So when we're shoving air in our engines or sucking it in our engines to get the oxygen to work with, we're also pulling a lot of nitrogen in. And the nitrogen is pretty stable, and it's a relatively inert gas. But when you get the temperatures high enough and the pressures high enough, it does react some. And we get some of the oxygen and the nitrogen combining together to create nitrous oxide. And there's common byproducts are NO, NO1, and NO2. And a lot of times the characteristics of those aren't different enough. In a lot of literature, you'll see those combined as NOx, because we don't care so much how many they are, but oxides of nitrogen. And they're not the best thing to have out there in the atmosphere, and there are some potential drawbacks to them. So when we start talking about the way we're managing our engine to create less harmful emissions, and what the EPA is concerned about, the big things they look at is, so I guess I'm going to start a new thing here, but as far as EPA concerns, the numbers they really look at are the unburned hydrocarbons, the CO, carbon monoxide, and the oxides of nitrogen. So those are the big things on EPA radar. I guess there's also, you know, there again, not a perfect world. Well, the fuel we have isn't straight hydrocarbons. There's additive packages, right? And some of those additives are designed to make the fuel more stable so that it doesn't evaporate and it doesn't turn bad. And some of those additives are things that naturally occur in the oil in the ground and aren't removed from it in the refining process. And so all of those little trace things wind up reacting to create some different things, but honestly, they're a really small percentage of what's going on, and we're not going to sweat them too much, but There's some aldehydes, there's ammonia, there's some carbolic acids, um, even in some cases, um, several other little things, but we're not going to sweat those too much. But just kind of wanted you to be thinking about what we're working with here: hydrocarbons and oxygen, and trying to get to here. Oh, and one thing I started to say, so the water um, we're creating it at a temperature where it's in what state? Solid, liquid, or gas? Right, water vapor, which is a steam. And we're creating it at such a high temperature that we don't realize it, but there's a lot of water vapor going out our tailpipes. And is that a harmful thing? You don't think so? I agree. um, but a lot of folks don't realize that. And you've probably seen, especially in cooler weather, you've seen water dripping out of a muffler or dripping out of a tailpipe. Um, well, kind of what creates that, um, crude art. But if this box here is our engine, and we've got a long pipe coming out of it to get to the back end of our pickup. And this pipe is all cold. We'll just say it's 30 degrees. And we're at this point coming out of our engine, we're dumping H2O that's at, we'll just say 1400 degrees. What happens to some of that 1400 degree water as it's traveling through this 30-degree pipe? Yeah. And when water cools down, or when water vapor cools down, what state does it turn? Liquid, yeah. Usually it doesn't go all the way to solid, but I'm not going to say it can't. But you're right, it goes to a liquid. So we'll wind up with some condensation, water droplets that form in here. And okay, if you got this can that's a muffler here, and you've got, and a lot of mufflers actually for this purpose will have a little drain hole in them. So now what happens once we've run this engine long enough that this 30-degree pipe is now, we'll just say 270 degrees. Do we get that condensation happening and water dripping out? Not as much as right. So at that point, it's still vapor coming out the tailpipe, so we don't see it anymore. So should we be too worried about that water dripping out of our muffler when the vehicle's only been running for 5 minutes? Nothing to be worried about. But if you don't understand that, you can say, whoa, what's this water dripping out of my pickup, right? If you see a lot of it, you might want to go make sure it's actually just straight water. Because there again, if we have a malfunction in the engine, we can be putting other things in that tailpipe that can be problems. But anybody got any questions about that so far? See, the bad thing about talking is I didn't get any of them goodies. So my wife brought goodies. So before we move on, any other questions about fuel and oxygen and so I'm going to go ahead and erase all this and talk just a couple of minutes about the different kinds of internal combustion engines. I guess I already said we're primarily going to focus on modern four-strokes. So I'll write that down. there's basically three kinds of, or very different types of internal combustion engines. I'm going to write down over here 4-stroke engines. Anybody able to think of a different type? Right, 2-stroke. And there's one more. Good guess. All good guesses, but none of them quite what I had in mind. There's rotary. So we're going to focus primarily on this one. And the reason for that being 99+% of all the automotive engines today are 4-stroke engines. And that may be an underestimation. It may be 99.9, I don't know. And the vast majority of engines we're going to encounter, you know, even on lawnmowers and stuff, are going to be 4-stroke. Now, chainsaws and weed eaters and some things like that run 2-stroke engines, some outboard engines. So we'll talk about those a little bit. But let's talk about, but like I said, we're over the 6 weeks, we're primarily going to be talking about these. And the handout that I gave you talks about the 4 strokes. So let's talk about those just a minute. So on our first, well, and you can start anywhere in this process because it's repeats over and over again, obviously. But on the handout, anyways, the first one is our intake stroke. So you can see there on your handout, I made some notes on the left side. I left room for you to make notes if you want to on the right side. So in my notes, you'll see I drew an arrow there. And that arrow talks about which way the piston is moving. Now, not all engines are oriented where the piston is like that, but the vast majority of them are. So we're going to talk about, and this shows an overhead valve engine, obviously, but with a spark plug. But if your engine's turned that way, which most of them are, although, you know, there's some that are laid on their side, and there's a rare few that have them going all the way around upside down. But anyways, this arrow is talking about an engine that's oriented like the picture. In the intake stroke, the piston is moving down. Let me back up half a step here. So for us to use this combustion, where we're taking a little bit of fuel and a little bit of oxygen and having this reaction that makes a rapid expansion of gases, we got to have a way to turn that gas into an action that we can use to do work. And so what we're going to do is we're going to try and contain it on the top, and we're going to put it in a cylinder, and then we're going to have a moving part down here that's connected to our machine. So that gas, that rapidly expanding gas, it's trying to go every which way and get out of there and come to atmospheric pressure. Well, we've got a head on top that we're not going to let it out that way. We've got a cylinder containing it on the sides. We're not going to let it out that way. The only way it can expand is to push on our piston. So that's why we got this moving part that we've got connected to our machine. Does that make sense? But in the intake stroke, that piston is moving down. Now, if we had all that closed up like I got it drawn, wouldn't be much point in moving that piston down. But if we make an opening here, what's happening when we move that piston down? It's sucking in air. Exactly right. And in some engines, the air and fuel are already mixed together. In some engines, we're sucking in just air, and then we're going to squirt the fuel in with a fuel injector. But anyways, we're going to fill this cylinder with air and at some point with fuel. So that's the intake stroke where we're sucking in the air. At the end of that stroke, we're going to close this back off. And when we close that back off, then we're going to start, what's the next stroke on your sheet? Compression. And in that compression stroke, we're going to run this moving piece, this piston, which direction? Up. Yeah. So what we're going to do, we're going to take this air we've got in the cylinder, and we're going to compress it. And one of the reasons for that is because, like we talked about in our chemistry part, the air we're working with is about 20% oxygen, and we need a lot of oxygen to make this work. And we're going to take this much oxygen and put it in, or this much air, which contains 20% oxygen, and put it in this much space, so that our reaction with our hydrocarbon will work better. And also that reaction works better when the temperature is higher than normal room temperature, and when the pressure is higher, that whole reaction works better. So we're doing three things there. We're increasing the pressure, we're increasing the temperature, and we're increasing the concentration of our oxygen. Does that make sense? So then that's our second stroke, is our compression. So now that we've compressed the air, and when we get to the induction part, we'll talk more about just how and we're mixing the fuel with it. But we've got that piston up here near the top, and we've compressed our air and our fuel. That's where we want to ignite it and have our combustion reaction. So at that point, if it's a gasoline engine, we're going to fire our spark plug. If it's a diesel engine, we're going to inject our fuel in, and we're going to have that combustion, and it'll push the piston down. And that's the whole point of the whole engine, is to push that piston down, and it's connected mechanically to the tires we want to move through 17 other parts, right? But that's the beginning of, what's it calling the third stroke on there, Joe? Power. So that's kind of the whole point of an engine, is to make power that we can use to do work. Either move our butt from here to yonder, or move a load from one spot to the other, right? So that's the whole point of what we're trying to do, is make this power stroke happen. And so then stroke number 4 is taking out the trash. So when the party's all over, you got to clean up the mess and put it in the trash can and pack it out, right? So at the end of the power stroke, we've used all that energy pushing the piston down. We're going to open a new spot over here, and we're going to push the piston up, and we're going to exhaust all the stuff that we're done using. We call it exhaust, right? So that's the 4 strokes in our 4-stroke engine. Now, as you can see, one of those is something we really want to happen on purpose and what we're working towards. The other 3 strokes, we're using some of that energy to make them happen. We've got a big weight called a flywheel that we've got spinning, and it's spinning our crankshaft, but it's taking some of the power from this power stroke to make all the rest of this happen. Just want you to kind of keep that in mind, and you'll see kind of how that works through some of the things as we go on. But keep in mind that in the 4-stroke engine, there's only one stroke that we're actually wanting to happen, and the rest of them are stuff we just got to do to make it happen. So in the 2-stroke engine, how are we getting rid of part of these? Well, I don't know how that works exactly. If we just keep having parties in here and keep building up the trash, boy, it don't take long and we can't even get in here, right? Boy, you got to take the trash out. What can we do away with? What's that? Well, you know, it'd be nice if we could. Sorry, guys, it's a trick question. We're not getting rid of any of them, but we're just trying to combine them and make them all happen in less time. So what we're doing, and this is, and encourage you to look at these after class if you got time. This I just brought for fun. This is a 2-stroke engine from a little model airplane. But this is a 2-stroke engine that's all tore apart. And there's no, so when we talked about our 4-stroke engine and we were opening and closing our combustion chamber, basically we've got valves where we let the intake come in when we wanted to and closed at other times. And we let the exhaust go out when we wanted to and closed at other times. Well, we're kind of faking it with some ports instead. So on the 2-stroke, the top half of our cylinder has no openings in it. But over here in the side, we're going to punch a hole in it. And over here on this other side, lower down, we're going to punch a hole in it. And then something we really haven't talked about a lot, but our crankcase is enclosed, and that is required on a 2-stroke. And we're going to have another hole in that over here somewhere. And we're going to throw a little pixie dust at it while we're at it. But what we're doing, the explanation of the 2-stroke makes a little more sense if we start in a different place in the cycle. So we're going to start at combustion. So 2-stroke, you're going to have the same kind of an idea, spark plug or a source of ignition. Anyways, let's start when we actually have our combustion. Is that okay? We're starting in a little different spot in the process. But we're going to have our piston up here, and we're going to go bang. And we're going to have the bang and push that piston down. Okay, are you with me so far? When that piston, so we've got all of our pressure and all of our gas pushing down on that piston to do the work we're actually wanting. When that piston gets down to this point, where this port's exposed, what's going to happen? Yeah. It's going to vent all that pressure out through this hole, and we're going to lose pressure, but it's taking the trash out, right? So then what happens when we get down to the point where our piston is sitting down here? And you know, I didn't, you know, fellas, I messed up with my drawing just a little bit here. And hopefully you won't fire me over it. Am I fired? Do I got to go? You want to let me slide with it? Okay, good. This is actually known as our transfer port. When you said, somebody said intake, and that was an obvious good guess, and it is how we get intake into the cylinder. But the intake into the engine as a whole is this port over here. But when you were talking about intake into the cylinder, you're exactly right. And most all two-strokes will be engineered where the shape of this transfer port and or the shape of the piston will try and create a flow in the cylinder. A lot of them will have the piston with a shape like this, or the shape of this port. It'll be contoured to direct the flow of the intake so that you get kind of a motion like this. When we're talking about imperfect world that we live in, the two-stroke is the next thing farther down the trail of imperfect, because the energy we're creating with that combustion, we're only using part of it before we get past this port, and we're wasting part of the energy we created. But we ain't having to open a valve. And through the transfer, we're pushing a mixture of air and fuel. And there may be one out there, but I'm not aware of it, that in the intake, by the time we're entering the crankcase here, we don't have three things. We've got our air, we've got our fuel, and we've got lubrication. If you'll bear with me, I'm just going to put oil, because that's what it is. But anyways, so we've got air and fuel and oil that we're pushing in through the transfer port and trying to create a swirl. And if we time all that just right, which we won't, it won't be perfect, but we'll get close. We'll push most of the exhaust out, and we won't push much of our air, fuel, and oil mixture out. Atmospheric pressure changes from one day to the next. The speed at which we run the engine changes all of that. So we're never going to hit that right on. But that's the idea is, now one thing that is unclear, the way I've been explaining this, but at the point we're at here, we've got air, fuel, and oil in this crankcase, and it's under pressure. Different two-strokes do it differently, but the vast majority of them are using the stroke of this piston to compress it. We're actually doing work on the bottom side of the piston. And let me show you something here, if you guys will pass this around. Most two-stroke engines will have something like this. This is a reed valve, and if you push it too far, you'll break it. But you can see, if we suck on this side, it lets it push in. You can look at it from the other side. So if we suck on this side, we can pull air through it. That makes sense? Not all two-strokes run this, but they'll all have some way of closing off the crankcase or pushing. So you guys see what I'm doing there? So we can go ahead and pass that around if you would. So that reed valve is basically a check valve here that lets air and fuel and oil come in, but won't let it go back out. And I'm sorry I interrupted myself in the whole flow of the strokes. But anyways, at the point where we're down low here, just trust me, you'll understand why later, but this is under pressure. And so the fact it's under pressure, we're pushing the air, fuel, and oil mixture up through this transfer port and trying to create a swirl in here and hope we get rid of most of the exhaust, but not too much of our new air, fuel, and oil mixture. Then we're going to start that piston going back up. So when it goes up to this point, it's got this transfer port. It's got the transfer port blocked off, so there's no flow there. Well, think with me just a second here. As that piston keeps going up and the transfer port's blocked off, what's happening to the pressure in here? Well, as the piston's going up, there's more pressure on this side, Joe. But what's happening on this side of the piston? It's decreasing. So with decreasing pressure, and that reed valve you were just looking at over here, what's going to happen at this point? We're sucking air in, right? We're sucking in our air, fuel, and oil mixture into the crankcase. So one of the things that's happening that allows us to run 2 strokes instead of 4 is we're using the backside of the piston to suck with. Does that make a little bit of sense? So as the piston's traveling up, we're sucking that oil, fuel, and air mixture in past that reed valve. But that reed valve's basically a check valve. It'll let it suck in, but it won't let it go back out. So we've closed off this port, but this one's still open. So we've still got some swirling action going on and some stuff going out at this point. But as the piston keeps going up, we'll get it past that point. And it's still going up. So what's going on at this point? Compression, exactly. So from the point where we close the exhaust port till we get the piston as far up as we want it to travel, or it mechanically can travel, we're compressing. So we're doing the same thing as the compression stroke here. We're compressing. Then when it gets all the way to the top of its stroke, we start over and we have our power. So it takes a little bit more to make all that all work, because we're trying to do 2 and 3 things at once, and we're using the back side of the piston to do part of it. So there's pros and cons. Everything's a trade-off, right? So let's talk about pros and cons here a little bit. Who can see a benefit to one over the other? That's exactly right. So our bearings in here, our bearings on our crankshaft, our bearings on our our wrist pin, those are being lubricated by the oil that's in that mix. So if we're just going to have a little bit of oil in our airflow, and it's going to be lubricating our bearings, or in our 4-stroke engines, not all of them, but the vast majority of them have a whole pan on the bottom full of oil, and we got a pump, and it pumps that oil up to all those bearings. Which one seems like it'll last better? Right. Long story short, forced lubrication with a pump that's going to pump oil on purpose into a bearing, it's going to last longer. So that's one of the reasons. We kind of like our cars to last. If we had an engine that croaked in less than 100,000 miles, none of us want to be real happy about that, right? So in things that we expect to last a long time, you don't typically see 2-stroke engines, because they're just where we're depending on the swirl of this. And don't get me wrong, there's a lot of engineering that goes into how that all swirls and is directed into those bearings. but still mixing a little bit of oil in the air that's flowing through it, it's just not going to lubricate as well, and so it's not going to last as long. So on our pros and cons, longevity is better over here. At the same time, I guess if you wanted to look at pros on this side, go ahead, Pat. Good question. Right. The biggest thing that happens when you're too rich, you've got too much oil up here where we're trying to have combustion, and we wind up fouling the spark plug and making a lot of our carbon that we talked about earlier, carbon and soot, that goops up the whole, well, the rings as well as the spark plug. And it'll also, when we're talking about pros and cons, we're like we was talking about, we're only using part of the energy in this, and so there's still a lot of compression energy when we open that exhaust port, which makes a lot of noise. So two-stroke engines are typically loud, and well, we put mufflers on, right? Plug the muffler up with all that carbon and unburnt oil. So when the mixture's too rich, you foul the spark plug, you schmutz up the rings. Schmutz, that's a real highly technical term, right? And you goop up the mufflers, and so they can't breathe and they can't spark, and you're yanking on the rope going, why won't this thing run? So that's what happens typically when they're too rich. And when they're too lean, like you said, you don't have enough lube to the bearings, and it all goes up in a cloud of smoke. It is. Well, when you take the mufflers off, and part of that too is timing. They're typically opening the exhaust valve a little on the early side compared to a lot of other engines. So there again, we still got a lot of that combustion energy that's whenever the exhaust valve opens going into that. And part of it is harmonics, because a lot of the engines we're dealing with in automotive, we will have even firing. So example, a 4-cylinder, 4-stroke engine that's in our Toyota pickup, or it's going to have a cylinder fire every 90 degrees of crankshaft rotation. Our V8 engines are designed, the throws in the crank are designed where we're going to have a cylinder fire on even. Harleys are a 60-degree V-twin. They got 2 cylinders. Between when this one fires and when this one fires, you've got a, let me think about that. You've got 210 degrees of crankshaft rotation. And then between this one, when this one fires and this one fires again, you've got 150 degrees of crankshaft rotation. So 210, 150, 210, 150, 210, 150. It's a real odd fire engine, if that makes sense. And that's a term you'll hear in engines is even fire and odd fire. Even fire means that there's an even number of crankshaft rotation degrees between when each cylinder fires. Those run smoother, have way less vibration, and are less obnoxious on our ears because they're smoother. Odd fire engines, Pop, 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 pop. Yeah, yeah. And if there wasn't a good flywheel to keep that whole thing going through all of these other 3 energy robbers, they wouldn't. Um, yeah, most of them are four-stroke. All of the single cylinders that, well, I shouldn't say that. Because, okay, your chainsaw is typically a single cylinder that's a two-stroke. But for example, like the ones I was talking about when I said pop, 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 our old Pop and Johnny John Deeres, they're four strokes. Um, and I guess my beautiful wife has pointed out it's 7 o'clock. And if anybody's got to go, it's cool. If you want to quiz now, it's cool. I've got a little bit more if you got time. Um, but I guess Wayne made a good point in that, there's some engines that are just way more obnoxious to our ears. And in general, two strokes are more obnoxious to our ears because there again, when that piston comes down past that exhaust port, the whole combustion process is in many cases only half done, and the other half is happening in this port and in our exhaust pipe, and they're noisier. But back to the whole pros and cons thing. One of the pros to this is there's a lot less moving parts. We don't have the valves in the head or in the block if it's a flat head, but we don't have these valves. The only valve is the reed valve. There's no camshaft, which a camshaft is what typically runs the valves in these. The number of moving parts and therefore the amount of mass that we've got to keep rotating when we're not making power is way less. And because there's a whole lot less rotating mass, we can run them at some crazy high RPMs. There are two strokes out there that run 15, 17,000 RPMs. It's not uncommon. A lot of the common two strokes will run 8 or 10,000 RPMs. We typically are going to run our four-stroke engines, depending on some of the design characteristics and what fuel they're using and stuff. We're going to run them 1,000 to 3,000 RPMs. But there again, we don't have to run them as many RPMs to get the power because we're using the whole stroke instead of exhausting it when we've only used part of that stroke. Because there's a whole lot less moving parts, these engines can be made a lot less weight. So one of the places you'll see a lot of two strokes is where weight matters, like in your chainsaw. We don't really want to have a 100-pound chainsaw. We don't even want to have a chainsaw that, has something like this little 3.5 horse Briggs. You'd get real tired of packing that thing. So with the two-stroke, there's so many less moving parts that we can make them a lot lighter weight. I guess another drawback to the two-stroke, they're typically less fuel efficient. If you look at amount of fuel burned versus the power we make, that ratio is much better with our four strokes, because there again we're using the entire stroke, not opening that port and dumping half of it out. What else? Anybody think of other pros and cons? There's one more big one that some people are real worried about. Emissions. What's that? Well, that's exactly right, Caleb. Eco-friendliness. Because to make this whole deal work, we're mixing oil in there, and we're burning the oil. There's a lot more of, you remember when we were talking about the chemistry, all these oddball things over here? There's a lot more of that oddball stuff in the two strokes, including the unburnt hydrocarbons going out, because like we talked about, that whole swirl we were trying to do and hope we got rid of most of the trash and didn't blow too much of our gas and air mixture out. That's a real imperfect thing. But anyways, between burning the oil and opening the port when our power stroke's half done and the whole swirl thing we're hoping to get right, there's a lot more things the EPA's unhappy about in a two-stroke. For example, I don't know, a few years ago, they made it where in Yellowstone you can't run a two-stroke snowmobile. All snowmobiles in Yellowstone have to be four-stroke. They are more eco-friendly. Just before we move on, anything else that you want to talk about there? Mm-hmm. It's not as big of an issue. There again, because we're running that stroke all the way down before we open an exhaust valve. And on this, we've done about 50% of the combustion before that piston comes down past that port. So half that combustion is being done in the exhaust. So there's more concern about it here, although you can have spark with either one. And in certain cases, you'll have regulations where spark arresters are necessary on both. You'll have a lot more regulations about that on the two-stroke because the combustion process is way less complete when we open the door to let it out. I'm going to talk real quick about these, not long. Rotary engines, there's just not a lot of them in use. They require an extremely high degree of precision to really run. The only one I'm even aware of, and don't get me wrong, fellas, I am the farthest thing from an expert on rotary engines. I'm going to share with you everything I know about them, and it's going to take 2 minutes. But you typically have kind of an oval-shaped cylinder, and it's not a cylinder like we think of here. It's laying down, and you're going to have kind of a triangle-shaped rotor that flops around in there, and it spins and rotates like that. And you're going to have a spark plug up here, and there's going to be some ports, and this thing's going to flop and roll in there. The benefit to these is with this piston in any of our piston engines, we're sending that piston one way, and then we're putting the brakes to it, and we're sending it the other way. And we keep stopping our motion and sending it opposite directions, which is a waste of energy. And these don't do that. This rotor in here just keeps spinning in the same direction. And as it flops in there, and flops not the technically correct term, but it'll rotate, and as it comes past one side, you'll have intake go in there, and then when it's more like and I'm doing a really bad job of drawing it, more like in this position where the spark plug's over here, then it'll have a it'll fire, and you'll have a power, combustion, and that rotor just keeps rolling in the same direction. But what you've got is on the tips of this rotor, you got to have as close to possible as a perfect seal, and that requires an incredibly high degree of precision and lubrication, and you got to have a big bag of pixie dust. But anyways, the other drawback to those is, and the reason, there was a very successful car. The Mazda RX-7 ran a rotary engine. People that had them, a lot of those people really liked them. They quit building them because they couldn't make the rotary engine pass emission. And a lot of the after treatment and pre-treatment and fuel management devices that have been invented to make the four-stroke, where the EPA lets us keep building them, they don't work on those. And that's the end of what I know about rotary engines. Anybody ever owned one? Um, so, but technically they are an internal combustion engine, so I thought I'd mention them. But if it's okay with you guys, we're going to focus primarily on the four-stroke, because that's really what all of our tractors, all of our trucks, all of our cars are going to run four-stroke engines. Does that make sense? I'll pass out the quiz. If you would like to participate in that, it would be fun. As you probably noticed on your way in the door, I didn't plan ahead well, and the Cummins engine that's cut apart out there won't fit through that door. Feel free to look at it. I can answer any questions, and feel free to look at the stuff I've got up here, and I can answer any questions. I'd be hard pressed to pick one, but I got two if that's okay, Wayne. One of them is metallurgy, but it's probably the smaller of the two. The whole metals industry has advanced a lot in making a lot of different alloys of metal that have some better wear characteristics than we used to have. But the biggest one is fuel management, by far. We'll talk a little more about this when we get into the induction section of our class, but when we were talking about our imperfect combustion, well, with carburetors like we ran forever, I had one instructor tell me that the only thing that will always be wrong is a carburetor. And it's true, in that carburetors never mix our air and Chasey? They never mix our air and fuel exactly the way we want them, but they get close. But because they're imperfect, we wind up with a whole lot of that stuff we would rather not have in our combustion process, in our chemical reaction. We wind up with a lot more acids, and we wind up with a whole lot more carbon. And you take that C12, C13, C14 carbon, and you put it between the piston and the cylinder wall, and you run it up and down, it wears out cylinder walls, it wears out piston rings. The acid going into our oils, of course, doesn't do great things for crankshaft bearings and erodes them over time. And so, as the fuel mixture devices have improved, so we're getting that air to fuel mixture more like we want it, and we have less of that oddball trash. That oddball trash was a lot of what wore out our engines, and the carbon more so than any of the others. But you know, we used to think that a pickup was wore out at 100,000 miles, and they typically were, because all that carbon running up and down between these piston skirts and the cylinder walls, and our rings in the cylinder walls wore them out, and coked up the valves where you couldn't get flow through them. And so getting that whole air fuel mixture right, so we have a lot less of those undesirable byproducts, is by far the biggest thing that makes them last longer. So along the lines of that, when we mess with that by putting race chips on our pickup that make them dump extra fuel, what's that do to our longevity? Shortens a lot. In some cases you do, but there again, the ones that make a lot more power, they don't mess with just the fuel. They try and shove more fuel and air, so that we're putting more of that in the cylinder, but we're keeping it balanced. And a lot of those cheap chips, all they do is dump some extra fuel. And that extra fuel does make more power, but it won't typically make a lot more power. But we're back to the thing where we don't have enough air. We're making more of that carbon, and that carbon, you'll see a lot more black nasties in the tailpipe, and you'll see a lot more black nasties here where we don't really want them, and it decreases engine life. Yeah, in general, yeah. What the chip is doing is saying, we don't like Detroit software that we're using to manage the fuel with, and we're going to do our own. Well, some of the guys that write those do a really good job. Some of the guys that write those, all they are thinking about is, we think it's cool to make a big black cloud that the guy behind us can't see through. Some of those guys don't do as good a job as others. So it depends on the guy writing that software and what's on the front of his mind. Is what's on the front of his mind making more power? Is what's on the front of his mind more fuel economy? Or is what's on the front of his mind drag racing? And different chips are made differently. But that's what they're doing, is they're overriding in. And see, the better chips are going to remove the factory software that, and all that software, it takes into account atmospheric pressure, RPMs, throttle position, a lot of things, trying to fine tune that air fuel mixture so we have really the right amount of oxygen and hydrocarbons. But at the same time, a lot of that factory software is painted by the EPA. And so some of it is written not for making the best power, but for making less oxides of nitrogen. Well, the guys that are doing a good job with those chips, they're still trying to do the best job they can of mixing the fuel and oxygen and take all of those parameters into account, but they're probably not caring quite as much about what the EPA cares about. But then you get the next one over here, and all he cares about is drag racing, and he thinks it's cool when he makes such a big cloud of black smoke that the guy behind him can't see the sun. Well, if that's what you want it to do, okay, but it ain't going to make your engine last well, and it ain't going to give you good fuel economy. And I sidetracked myself a little bit, but the better chips are going to remove that factory software and replace it with other software that does all those calibrations. A lot of the cheap chips are an interference box, is one of the ways they're described. So they'll have wires going to a manifold pressure sensor, and they'll have wires going to a fuel pressure sensor, and those wires come into this box and then go back out to the wires that used to go from those sensors to the computer. And all they do is lie about the sensor readings. So they'll take this manifold pressure sensor reading and reduce it by 2 psi. So whatever the actual manifold pressure is the computer, what it sees is 2 psi lower. And the same thing on the fuel pressure. And so it's just lying about those readings to the computer, but the computer's still running its normal calculations. Any of the chips that cost less than about $300, they're just those interference boxes, and they're marginally beneficial. And I will say that probably at least, and this may be a low guess, but at least 25% of the time when a pickup gets towed into our shop and it's dead on the hook, won't run, we unplug the interference box, chuck it over our left shoulder, plug the factory wires back into the factory sensors, and start the truck and drive it out of the shop. The guys that are doing the research and doing due diligence to really come up with a complete new calculation of how we're mixing the fuel and are replacing factory software with their own software, they don't work cheap. And those kind of things typically start at $500 and go up. That's a broad generalization, but it's mostly true. Yeah. So sorry about the long-windy answer. Well, long story short, I would not recommend buying any of the ones that cost less than $500 because I haven't seen one yet that I would recommend. On the more expensive ones, what a guy really needs to do, well, I guess the best thing I know to do, maybe is a better way to put it, Pat, is go to some of the websites that sell those and look at the feedback of people that have bought them and look at their comments. Was the comment from a kid and he said, "Wow, it made the huge cloud of black smoke, I'm thrilled." That's what you want, that's the chip to buy. On the other hand, if the feedback from people that bought them are a bunch of guys that are either negative feedbacks from kids like that, "Man, this thing didn't make no black smoke, I hate it, it stinks." And the next feedback was from a guy that, "Hey, I'm pulling a big trailer and this thing did what I wanted it to and I'm getting good fuel mileage." Well, if that's what you want. And so I hate to say it, but that's the best thing I know to do, unless it's a chip that some of us have experience with, is you read those feedbacks and look at what those comments are. Not just are they positive or negative, but is the positive comment, what's he saying there? What did he get out of that chip? And is it the same thing you want to get out of it? Or is it something different than what you want to get out of it? That's the best. There again, it kind of depends on the guy that wrote that software. In general, if you've got one of the chips that has 5 settings, um, setting 3, 4, and 5 are going to be for racing, making big clouds of black smoke. This is a broad general statement, but there again, mostly true. The chips that have a tow setting, if they have that, that's the setting we've seen people be most happy with. Because and there again, this is not going to be 100% true, but if they have a setting that's labeled as tow. Now, if they only have 1, 2, 3, 4, and 5, this probably ain't going to be true. But if they have a setting that's labeled as tow, in general, most of those are going to be settings that try and optimize the fuel and air mixture to make good power and make good fuel and ignore the EPA. And those tend to be the ones that we see folks that are there again trying to pull heavy trailers and get good fuel mileage be happy with. In general, the ones that just have 1, 2, 3, 4, and 5, not so much. So if you haven't got a goodie, why, feel free to grab one of those on your way out the door. And if you would, just if you want to turn in the quiz, why, let's make a pile of those right here. And if you want to, why, we can go turn the crank on that display outside and look at the 4 strokes if you want to. Feel free to look at all this stuff and ask questions too.